Okay. So again, welcome back to another session of Gate Live sessions. This for today's session also we'll be trying to solve some more questions from chemical reaction engineering, the basics of CRE1 basically. So it will involve the design of batch reactors, ideal case PFR and CSTRs, and Arrhenius theories, activation energy, and all the basic reaction rate, kinetics, reaction constants, and so on. So today we'll be trying to do that. So let's get on with the first question for today. So this is a question from GATE 2022, the most recent GATE. An elementary irreversible gas phase reaction A gives B plus C is carried out at a fixed temperature and pressure in two separate ideal reactors. Case 1 is a 10 meter cube plug flow reactor. Case 2 is a 10 meter cube continuous stir tank reactor or CSTR. If pure A is fed at 5 meter cube per hour to the PFR operating at 400 Kelvin, the conversion is 80%. If a mixture of 50 mole percent of A and 50 mole percent of an inert is fed at 5 meter cube per hour to the CSTR operating at 425 Kelvin, the conversion is again 80%. The universal gas constant R is taken as 8.314 joule per mole per Kelvin. Assuming Arrhenius rate law, the estimated activation energy is dash in kilojoule per mole, rounded off to 1 decimal place. Okay, so if you go through this question, so basically in this question, what they have said is they have given us a gas phase reaction, A gives B. So in this gas phase reaction, this is carried out in two separate cases, one in a PFR of 10 meter cube volume, the other is a CSTR which is again of 10 meter cube volume. And the difference here is the reaction that is conducted in these PFR and CSTR. So in PFR it is conducted at 400 Kelvin and in CSTR it is operated at 425 Kelvin. And they have also said that the conversion is same for both these reactors. Okay, the differences between these two reactors is one, the operating temperature. So in PFR it is 400 Kelvin, in CSTR it's 425 Kelvin. And what they want, and also the other difference is that in PFR they have fed the reactor with pure, stream of the reactant A. But in the case of CSTR, they have added 50 mole percent of an inert substance with the, reactant A. So with these two differences, they want us to calculate the estimated activation energy for this reaction to occur. Okay. So how we can proceed is by looking at this, data that they have given. So there are two cases, and they have given us a lot of data as well to find the activation energy for two different, temperatures. So you can actually not apply this to other questions where they have asked you to, apply Arrhenius or any other, theories for temperature dependency, like the, transition state theory or those kinds of collision theory. So you can see if they have given two temperatures and they have asked you to calculate the activation energy, the first thing you need to see is whether you have the temperatures first, and they have the temperature given here. The other thing you need to know is the rate constants, K1 and K2. So if we see this question, they have not given us K1 and K2. So our objective here is to find this rate constant for these two cases. So let's say rate constant K1 is the case of PFR, and rate constant K2 is the rate constant of the reaction in CSTR. So if we find these rate constants K1 and K2, we can apply this Arrhenius law and we can find the activation energy. So that is how we will proceed with this question. Okay. So let's take case 1 as the PFR case. So they have given us all these data. So they have given the volumetric flow rate as 5 meter cube. They have given the volume, 10 meter cube. They have given the conversion as 0.8 and the temperature also as 400 Kelvin. So one thing we need to note here is it is a gas phase reaction. So gas phase means it's a variable volume system. Okay. So for variable volume system, we need to find the epsilon. So we'll find the epsilon like this. So we can write the reaction A gives B plus C, and we can find the epsilon as the total moles of product minus total moles initially fed by total moles initially fed. So total mole of product is 1 plus 1, that is 2, and total moles initially fed to the reactor. In the case of PFR, it is only pure A. So it is 1. So 2 minus 1 by 1, and the epsilon will be 1. Right? Now the same thing we need to calculate for CSTR. So for CSTR, again they have given us the data which is pretty much same as in the case of PFR. The only difference is the operating condition, which is at 425 Kelvin. And the other difference is the feed. So the feed they have given as 50% A and 50% inert. Right. So based on this, we need to find the epsilon with this difference in the feeding. So the reaction now, the equation of the reaction becomes A plus inerts giving B plus C plus inerts. So basically the reaction here is A gives B plus C, but then the inerts that is fed into the system will again come out into the product phase as inerts itself. So now what happens is the epsilon will be the number of total moles of product. So here now the total moles of product will be B plus C plus inert. So that means it is 1 plus 1 plus 1, and that is 3 moles. And total moles initially fed will be A plus inerts. So that will be 1 plus 1. So that will be 2. So epsilon here will become 3 minus 2 by 2, and that will be 0.5. Okay, so these are the two different values of epsilons. So one is the value for PFR and the other is for CSTR. Okay, so now we can proceed to find the rate constants. So they have said that this system follows Arrhenius law. So by Arrhenius law, we have the equation K is equal to K0 e raised to minus E by RT. And if we take the ln of it or the log of it, ln K1 by K2 is equal to minus E by R into 1 by T1 minus 1 by T2. Okay, so what we need to find here is we need to find this K1, we need to find this K2, and then we need to find this activation energy minus E. They have already given us the data for T and T1 and T2, and R is also given as 8.314. So to find K1 and K2, we need to apply the design equations for PFR and CSTR. Okay, so that is how we will proceed to find the rate constants in the case of PFR and CSTR. And after finding the rate constants from the respective design equations, we will substitute those rate constants back into this Arrhenius equation, and then we will find the activation energy. Okay, yeah. So let's see how we can find the rate constants. Just a second. Okay. So now case 1. So we'll move to find the rate constants of PFR first. So case 1 is PFR, and we have the design equation for PFR. Tau is equal to V by nu 0, which is equal to 0 to XA CA0 dXA by minus RA. So we have all these data here. We have the value for V, we have the value for nu 0, we have the conversion XA. We we need to find this K here of the rate equation. Okay. Now again, this is a gas phase system, so we need to accommodate epsilon as well into the equations. So here the design equation will become V by nu 0, which is equal to Ca0 into integral 0 to Xa dxa by Kca, and this Ca will be Ca0 into 1 minus Xa by 1 plus epsilon A Xa. Okay, and we found that epsilon A here is 1. So Ca will become Ca0 into 1 minus Xa by 1 plus Xa, and we will substitute this Ca here back into this design equation, and now what we have to do is integrate this equation. So V by nu 0 is equal to Ca0 into 0 to Xa integral dxa by K Ca0 into 1 minus Xa by 1 plus epsilon A Xa, which is 1 plus Xa, and we can cancel out this Ca0 and Ca0. So now what we have to do is rearrange this and integrate this equation, and this integration becomes K tau is equal to, or Kv by nu 0, which is equal to 1 plus epsilon A into ln 1 by 1 minus Xa minus epsilon A Xa. Okay. Yes. So this is actually used as a standard equation also for first order variable volume systems. So you can even like make a note of it. If you guys even have any doubts regarding this integration, we can even go through that. So this is a standard equation for first order reaction. Yeah. So it's a standard equation for first order reaction, and from this equation we have the values, all the values here except for K, which is K1 basically. So now we'll just have to substitute all these values, and we'll find the value for K1, which is 1.2. Okay. Now we do the same thing again for CSTR. Okay. So for CSTR, we had epsilon is equal to 0.5, and we have the design equation, which is tau is equal to V by nu 0, which is equal to Ca0 into Xa by minus Ra. Now again what we have to do is we have to substitute minus Ra is equal to Kca, and this Ca will be Ca0 into 1 minus Xa by 1 plus epsilon A Xa, and epsilon here is 0.5, so 0.5 Xa. So all we have to do is substitute for minus Ra is equal to Kca, and Ca for Ca0 into 1 minus Xa by 1 plus Xa, 1 plus epsilon A Xa. Now substitute it and substitute all the other values as well. So we have the values for B, we have the values for nu 0. So substitute all these values and rearrange it, and we'll have K is equal to 5 by 10 into 1.04 into 0.8 by 0.2, and this is basically K2 for CSTR. So this K2 will be 2.8. Okay. So we can even, to avoid confusion, we can even write K. So this is K1, which is at 400 Kelvin, that is 1.2 for PFR, and this is K2, which is K at 425 Kelvin, and that is 2.8, and this is for CSTR. Okay. Now we have both the values of the rate constants K1 and K2, or the rate constants at 400 Kelvin and 425 Kelvin. Now all we have to do is substitute these rate constants values back into the Arrhenius equation and find the activation energy. Okay. So by Arrhenius law, ln K K1 by K2, or here to avoid confusion I have written it as K 400 Kelvin by K 425 Kelvin is equal to minus E by R into 1 by 400 minus 1 by 425. Okay, so this is basically the form like this, ln K1 by K2, which is minus E by R 1 by T1 minus 1 by T2. So we saw that this is the general equation for Arrhenius law. We just substituted all these values in this equation. Now just substitute all these values here, and we can solve this equation for E. So K 400 is 1.2, K 425 is 2.8, and that is equal to minus E by R, which is 8.314, into 1 by T1 or 1 by 400 minus 1 by T2, which is 1 by 425. Now all we have to do is rearrange this and solve for E, which is the activation energy, and we'll get the activation energy as 47,902.2 joule per mole, and they have asked us to find the value in kilojoule per mole. So we'll get the value approximately as 47.9 kilojoule per mole. Okay, so the right answer for this question lies in the range between 47 to 49 kilojoule per mole. Okay, so this is how we solved this question. So what we did, we first found out the epsilons, because this is a gas phase reaction. So we found out the epsilon which is needed to accommodate for the change in volume of this gas phase reaction. So we found the epsilon for both CSTR and PFR. Then we found out the rate constants for CSTR and PFR using their design equations. And once we had the rate constants from the design equations, we substituted those rate constants into the Arrhenius equation, and we just had to solve one equation and find activation energy E. Alright. Is this clear? Okay, fine. So yeah, like this is a bit lengthy question, and like you can actually expect such questions from CRE for your numerical type questions in GATE. So, but again, this is actually a straightforward question. So once you find what values you need to find in order to to find the answer, you can just proceed. So here all you need to recognize is that you need to find the rate constants for PFR and CSTR. Once you recognize that, now you have all the tools to find the rate constants. You have the design equations for PFR and CSTR, and you find the rate constants, and then using those rate constants you find activation energy using Arrhenius. Okay, let's move on to next question. Just 1 second. Just read through this question. Just give me 1 minute. I'll just put this for charging. And So now we are looking at a question from GATE 2020 in chemical engineering, question number 24. The decomposition of acetaldehyde, which is X, to methane and carbon monoxide follows four-step free radical mechanism. The overall rate of decomposition is of X is minus Rx is equal to K2 into K1 by 2K3 the whole raised to 1 by 2 into Cx raised to 3 by 2, that is equal to K overall Cx raised to 3 by 2, where K1, K2, K3 denotes the rate constants of the elementary steps with corresponding activation energy in kilojoule per mole of 320, 40 and 0 respectively. The temperature dependency of the rate constant is described by Arrhenius equation. So Cx here denotes the concentration of acetaldehyde. The rate constant for the overall reaction is K overall, and the activation energy for the overall reaction in kilojoule per mole is dash. So this is a question from CRE, and the reference NPTEL lecture can be found in week 1, lecture 3, kinetic model and temperature dependency, chemical reaction engineering 1 by Professor B. Mandal, Department of Chemical Engineering, IIT Guwahati. Okay. So here they have given us a rate equation. So in this rate equation, they have said that this reaction happens in a four-step free radical mechanism, and this rate equation has three rate constants K1, K2 and K3, and which is denoted as K overall as well. And using these data, they have also given us the activation energy for each of these steps. So step 1 has an activation energy, or K1 has an activation energy of 320, K2 the associated activated energy is 40, and K3 the associated activated energy is 0. So from these data we need to find the overall activation energy, or the activation energy for the overall reaction, right? So let us write the rate constants that is given here. So K overall is equal to K2 into K1 by 2K3 the whole raised to 1 by 2. Okay, and they have said that this rate constant follows Arrhenius equation. Okay, so by Arrhenius, K is equal to K0 e raised to minus e by RT. So what we have to do here is we have to substitute this Arrhenius law into these K1, K2 and K3. So let's see how we can do that. So K2 into K1 by 2K3 the whole raised to 1 by 2. So this is, let's say this is K20 e raised to minus E2 by RT into K1, which will be K10 e raised to minus E1 by RT by 2 K30 e raised to minus E3 by RT the whole raised to 1 by 2. Okay. So this is equal to K overall into e raised to K0 overall into e raised to minus e overall by RT, right? So now what we can do is we can equate the exponential terms. So e raised to minus e overall by RT will be equal to e raised to minus e2 by RT into e raised to minus e1 by RT by e raised to minus e3 by RT the whole raised to 1 by 2. Okay. Now we just have to simplify the right hand side. So we can write this as e raised to minus e2 by RT plus minus e1 by RT, and this is raised to 1 by 2. So minus e1 by 2 RT minus of e3 by 2 RT. So this will be equal to e raised to minus e overall by RT. Okay. So what we did here is we just equated the exponential terms. So first what we did, we we rewrote this rate constants in terms of their frequency factors k0 and exponential terms e raised to minus e by RT, and we just equated the exponential terms with each other. And now all we have to do is simplify this right hand side. This will be e raised to minus. Now what we can do is we can apply the values as well. So they have given that E1 is equal to 320, then E2 is equal to 40, and E3 is equal to 0. Okay, so what we can do is we can substitute these values here. So e raised to minus 320, sorry, okay, okay. So now what we can do is let us first equate the e terms. So again, e raised to minus e overall by RT is equal to e raised to minus e2 by RT plus minus e1 by 2 RT minus minus e3 by 2 RT. Now just take the ln in both sides or equate the exponential terms itself. We will be having minus e overall by RT is equal to minus e2 by RT plus minus e1 by 2 RT minus e3 by 2 RT. So we can cancel RT on all the sides. So minus e overall will be minus e2 minus e1 by 2 plus e3 by 2. Okay. So we have the values for E1, E2, E3. So E1 is 320, E2 is 40, and E3 is 0. Now all we have to do is just substitute these values here. So minus E overall will be minus E2, which is minus 40, minus E1 by 2, that is minus 320 by 2, and E3 is 0, so it will get cancelled. So this is basically minus 40 minus 160, and that is minus 200 kilojoule per mole. Now this doesn't stop here. This is the value for minus E. So we need to find E overall, which is the reverse sign of this, basically 200 kilojoule per mole. So this is the answer here. So here what we did is we just took the overall rate constant, we equated the overall rate constants to its given K1, K2, K3 form. We expanded this rate constants K1, K2, K3 into the Arrhenius forms, and we equated the exponential terms of that expansion. And once we equated that exponential terms, it is easier to solve. We just had to do some mathematical operations to it, and finally we'll arrive at the value E overall as 200 kilojoule per mole. Okay, so is this clear? Okay, fine. Um, Let us move on to one more question. This one. Fine. So now we are looking into GATE 2020 question, from chemical engineering, question number 44. An elementary liquid phase reversible reaction P reversibly gives Q is carried out in an ideal continuous stir tank reactor or CSTR operated at steady state. The rate of consumption of P, which is given as rate of P or minus Rp in mole per liter per minute, is given by minus Rp is equal to Cp minus 0.5 Cq, where Cp and Cq are the concentrations in mole per liter of P and Q respectively. The feed contains only the reactant P at concentration of 1 mole per liter, and conversion of P at the exit of CSTR is 75% of the equilibrium conversion. Assume that there is no volume change associated with the reaction, and the temperature of the reaction and the temperature of the reaction mixture is constant throughout the operation. The space time in minutes of CSTR is dash rounded off to 1 decimal place. So this question is based on the design of mixed flow reactors, and the reference NPTEL lecture can be found in module 1 lecture 17, design of mixed flow reactors, chemical reaction engineering 1, homogeneous reactors, by Professor K Krishnaya, Department of Chemical Engineering, IIT Madras. Okay, so let us write down the data they have given us first. So first they have given the rate equation minus Rp is equal to Cp minus 0.5 Cq. Okay, they have given that the initial concentration of Cp or Cp0 is 1 mole per liter. Also they have given that the conversion of P xp, this is 75% of equilibrium conversion x eq. Now what we need to find here is the space time. Space time tau is what we need to find here. Okay. Now let us start with the equilibrium conversion. So for equilibrium conversion, we have this equation P reversibly gives Q. At equilibrium, the conversion will be equilibrium conversion, and at equilibrium rate of reaction or minus Rp will be 0. Okay, so we have a rate equation here, Cp minus 0.5 Cq, and this will be 0 at rate equilibrium. Okay, so now we can rewrite this. So this will be Cp by Cq is equal to 0.5, right? So for constant volume system, so here it is given that it is a constant volume system. So for constant volume system, Cp can be Cp0 into 1 minus Xp, and this is at equilibrium. So this will be Xp equilibrium. Okay. On the other hand, Cq will be Cp0 into Xp at equilibrium. So what we are trying to say here is the final concentration of Cp will be whatever P that is remaining after the conversion of P at equilibrium, and the final concentration of Q will be whatever P that got converted into Q for the given equilibrium conversion, right? So we just substitute these two equations on top. So Cp by Cq will become Cp0 into 1 minus X equilibrium or Xp equilibrium by Cp0 into X equilibrium, and that is equal to 0.5. So Cp0 and Cp0 will get cancelled, and now this is just one variable that is remaining, that is X equilibrium, and we can solve for this X equilibrium, and X equilibrium will be 0.5. Okay, now the data they have given that the conversion, the actual conversion in the system, that is 75% of X equilibrium. Okay, then Xp will be point. Okay, I made a mistake here, sorry. A small calculation mistake from my part. Okay, so solving this, the X equilibrium will be 0.667, or this is approximately 2 by 3. So this will be X equilibrium, and the actual conversion, they have said that actual conversion is 75% of X equilibrium. So that means actual conversion Xp is equal to 0.75 into 0.667, and that will be approximately 0.5. So the actual conversion here is 50%. Right. So far what we have done is we took the rate equation at equilibrium, and we try to find the equilibrium conversion for this given reaction, and we found the equilibrium conversion to be 2 by 3 or 0.667, and from that we found the actual conversion Xp as 75% of equilibrium conversion, and that is equal to 0.5. Now we can go with the design equation for CSTR. So for design equation, tau is equal to Cp0 minus Cp by minus Ra. So what we need to find here is the space time tau. So now all we have to do is just substitute all these values. So we have the value for Cp0, we can find the value for Cp, which is Cp0 into 1 minus Xp. Okay, so this is 1 into 1 minus 0.5, and that will be 0.5 because Cp0 has been given as 1. So Cp will be 0.5. Then Ra, this is given as Cp minus 0.5 Cq. So we just found out the value for Cp. Now we need to find Cq. So Cq will be Cp0 into Xp, and that is again 1 into 0.5, and that is 0.5. Okay. Now all we have to do is substitute all these values in the design equation. Tau is equal to Cp0 minus Cp by minus Ra, and that is Cp0 minus Cp by Cp minus 0.5 Cq. So we have Cp0, that is 1, Cp as 0.5, then again Cp 0.5 minus 0.5 into Cq, which is again 0.5. Now all we have to do is just calculate for this tau. So the space time tau will be 1 minus 0.5, that is 0.5 by 0.5 minus 0.5 into 0.5, that is 0.25. So this will be 2 minutes. Yeah. So this is how we can solve this question. So what we did here is basically we needed to find the space time tau, and for the space time tau we needed one data which is basically conversion. Okay, because we didn't have the actual conversion here. So to find the conversion, they have given one data that the original conversion is 75% of the equilibrium conversion, and we can find the equilibrium conversion like this. Okay, I hope this is the right page. Feel there is a lag between this screen and this Google Meet. Okay, fine. Okay. Can anyone say like what page are you able to see in the Google Meet? Is it the final answer page or is it the any other page? Guys, like did you understand what I was asking? Are you able to see the final answer here in this page, or this is the page where we did the conversion and all? Like I feel there is a lag between my screen and this Google Meet screen. So that is why I just wanted to confirm. Middle page, okay, fine. Yeah, okay. Yeah, so there seems to be a lag between the screen. Fine, that is fine. Okay, now it's fine. Okay. So yeah, so basically what we did here is we first found out the actual conversion by using the equilibrium conversion. And once we found out the actual conversion, it is just a straightforward mechanism. We just had to substitute all these values in the design equation for CSTR, because we are using a CSTR here, and just solve that to find the space time, which is 2 minutes. Okay, like is this clear? Like, do you guys now understand how we solve this? If there is any part that you want me to explain again, feel free to tell me. Or if this is clear, we can move on to just one more question. So this question was actually a doubt someone asked last time. Okay, fine. Okay. So I think it was Harshal who asked this question, right? Regarding the unit of rate constants. Am I right? Or was it someone else? Yeah. Uh, yeah, Harshal, you are here, right? Okay, fine. We'll actually try to look into the question that you suggested last time. Um, where is it? Okay, okay. So, yeah, let's see how we can proceed with this question. So just read through this question. So, this is a question. Um, one second. Okay. So now we'll be looking into a GATE 2005 question from chemical engineering, question number 67. The rate expression for the reaction A is given by minus Ra is equal to K1 Ca square by 1 plus K2 Ca raised to 0.5. The units of K1 and K2 are respectively, and the four options given are as follows. So this is a question from kinetics from CRE, and the reference NPTEL lecture can be found in week 1, lecture 2, kinetics of homogeneous reactions, chemical reaction engineering 1 by Professor B. Mandal, Department of Chemical Engineering, IIT Guwahati. So in this question, they have given us a certain rate equation, and we are asked to find the units of K1 and K2 respectively. So let's see how we can proceed with this. The first thing you need to remember is the rate of, the units of rate of reaction. So unit of minus Ra, this will be mole per meter cube second. Okay. So unit of minus Ra is basically mole per meter cube per second. So if left hand side minus Ra is mole per meter cube per second, the right hand side should also satisfy this unit. Okay. So that is the first thing that we need to note here. Now the second thing, they have given that the rate equation is K1 Ca square by 1 plus K2 Ca raised to 0.5. Now if we look at this denominator alone, 1 plus K2 Ca raised to 0.5. This 1 is basically a constant. That means this is basically unitless. So there is no unit for this. So in order for this addition to make sense, this term K2 Ca raised to 0.5 should also be unitless. Okay. So let us see. So yeah. So K2 Ca raised to 0.5 should also be unitless. Okay. Let's say this is 1. So we have the unit of Ca. Unit of Ca is basically mole per meter cube, right? So unit of K2 into mole per meter cube, the whole raised to 0.5, is basically unitless, or let's say 1. So that means unit of K2. So what we can do is we can take this mole per meter cube term this side. So this will become meter cube per mole raised to 0.5. Okay. So basically what we are saying is unit of K2 should be, so we'll take this denominator mole to numerator, mole raised to minus 0.5 or minus 1 by 2 meter cube raised to 3 into 0.5 or the 1.5, that is 3 by 2. So this should be unit of K2. Okay. So in this in these options, so in these options, um, option A basically has this unit mole raised to minus 1 by 2 meter raised to 3 by 2, and also option B also has this. So we can't just proceed with the unit of K2. So what we'll do, we'll find the unit of K1 as well. So as I said, this whole unit is the reaction rate unit. Unit of minus Ra is equal to K1 Ca square by 1 plus K2 Ca raised to 0.5. This whole unit has to be mole per meter cube second inverse. Okay, we just said that this denominator is unitless. So that means this numerator should also have this unit. Okay, so that is the final thing that we need to remember, and using this concept we can find the unit of K1. So K1 Ca square is equal to mole per meter cube second inverse. Okay, again unit of Ca is mole per meter cube. Then unit of Ca square will be mole per meter cube the whole square. Right. So let us proceed with this. Okay. So yeah, K1 Ca square should be mole per meter cube second. So K1 into mole per meter cube the whole square will be mole per meter cube second. So now what we can do is we can just take this unit of Ca square to this side. So unit of K1 will be mole per meter cube second by mole square by meter cube square. Now all we have to do is just solve for this. So mole and mole gets cancelled, meter cube and one of the meter cubes gets cancelled, and this will become meter cube per mole second, or basically unit of K2 is equal to mole raised to minus 1 meter cube second raised to minus 1. Okay. So now we look for this, unit of K1. So now we'll look for this in the options. So option A suffices this these units. So option A, from option A, K1 is mole mole raised to minus 1 meter cube per second inverse, and K2 was mole raised to minus 2 mole raised to minus 1 by 2 meter raised to 3 by 2. So option A, option A suffices these two units. So option A is the right answer. Okay. So Harshal, is this clear?
Sir, how to identify the term is unitless or unit denominator terms?
Um, if you see any number in the denominator, so here you saw, like, K1, let's say, it is 1 plus K2 Ca raised to 0.5. This is given here. This this one is just a number. Okay, this one is basically unitless. So let's say, instead of this, you have a reaction rate equation like K1 by 2 plus K2. Okay, this usually you won't get. Okay, 2 plus K2 Ca square or something. Okay, now it is fine. So let's say you have a reaction rate equation like this. Then again, this 2 is unitless. Basically, any number you see in a rate equation, it should be unitless. So that is why, usually you would, yeah, okay, I'll just write a new page. Okay, so here it was minus Ra is equal to K1 Ca square by 1 plus K2 Ca raised to 0.5. So any number, if you see in the denominator of a rate equation, that is basically unitless, no matter how big the number is. This is one of the reasons, like, it is very, very rare that you see a rate equation which is, minus Ra is equal to 1 plus some K Ca raised to 2 or something like that. It is very rare you see such an equation for it, because this one is basically unitless, right? But if at all you do see such rate equations, then you have to assume this one has a unit of this unit as same as this reaction rate. Only if you see any number in the denominator. So like in this case, this K1 Ca by 1 plus K2 Ca. Only in these kinds of scenarios, it is safe to assume that this one is unitless. If it appears in the numerator, or if it appears like in this case, minus Ra is equal to 1 plus K Ca square or Ca cube or whatever, then this one definitely has a unit. Okay, because for two sides to be equated, the units should be of the same. So this is what you learn in the dimensional analysis, I think in transport phenomena as well. So for two substances to be equated, their units has to be same, right? So that is the concept here. Do you want me to explain it again?
Thank you, sir.
Okay. So yeah, again, like, basically, just if you see any number in the denominator of a rate equation, that is basically unitless. Only if you see a number on the numerator, or if there is no denominator and then there is a number like this case, then that number has unit. And then also you can apply the same concept here. Unit of this rate, which is mole per meter cube second. This should be equal to right hand side as well, mole per meter cube second. So then this one should have the unit of mole per meter cube second, and this Kca square will also have the unit of mole per meter cube second. Okay, so basically that is the concept that we are using. Only if the number is in a denominator, you can take it as a constant with no units. Fine.
Okay, sir.
Okay. Okay, we'll stop here. So I hope this session was useful, somewhat. I think we solved 4 questions today. We'll continue this for some more classes. I'll see if we can find more questions from previous year gate regarding this design of batch reactors and rate kinetics and everything. And hopefully in the coming classes, let's say after 2 or 3 classes, we'll go into non-ideal reactors and catalysis. Fine. So thank you for joining, and I'll see you guys next Monday.